Okay, gang. Welcome to CSC 475. We're starting to come into the home stretch here. Today what we're going to be doing is we are going to be looking at logic again. We're going to still be looking at propositional logic today. But what we're going to do is we are going to look at a kind of a standard form called conjunctive normal form. And conjunctive normal form is a standardized way of representing a whole bunch of logical statements. And we use conjunctive normal form because it allows us to implement an automated reasoning technique called resolution. Resolution is a very simple technique that basically involves matching and canceling of terms. And we're going to go through the details of it, but it's very, very straightforward and simple to do. Even a computer could do it. It is a reasoning technique that subsumes modus ponens, modus tollens, and chaining of implication. In other words, it can do all of the things that can be done by those three. So resolution can do effectively chaining of implication, it can effectively do modus ponens, and it can effectively do modus tollens. So really you only need one simple rule called resolution if you have your logical argument in conjunctive normal form. So we're going to introduce that. We're going to introduce resolution. We're going to introduce something called resolution refutation proofs, which is a proof by contradiction strategy that you can use with resolution to prove certain things. And then we're going to talk about something called horn clauses and horn clause notation. And the reason we're going to talk about horn clause notation is that forms the basis of the programming language Prolog. Prolog's an interesting language. It's not really used very much anymore, but it's an interesting language in that it was an attempt, it was a first generation attempt to build a language in which you specified what needed to be done and let the computer system concentrate on how to do it. So normal programming, when you write algorithms, you are writing exactly how to solve the problem. When you write a specification, you're writing sort of a what, right? Well, Prolog was a very early attempt to write a programming language where you would write the what in logic, and you would let the underlying theorem prover solve the problem for you. Now it's first generation. It was, you might say, a partial success, as you guys will see. So that's what we're going to do today. And then on Thursday, we're going to expand everything that we've talked about to what's called first order logic. First order logic allows us to implement variables within our, right now we have propositional variables. We have propositions, and that's all we have. Well, in predicate logic and first order logic, you can, it's a more general system that lets you kind of, yes, maybe we would say let you talk about categories of things rather than just individual things. If propositional logic only allows you to talk about individual things, first order logic or predicate logic, as it's called, lets us talk about groups of things. So we'll do that on Thursday. And then on next Tuesday, our last lecture, we're going to go back and we're going to actually look at Prolog a little bit, because it is a fun little language to look at. And I wasn't sure, if you check the syllabus, you'll see that I don't have Prolog listed this quarter, because I wasn't sure if we would be able to get to it. But I think now we will be. So that should be Tuesday. And then, of course, our exam will be a week from Thursday. That'll be our final. Those of you who are graduating, I've touched base with most of you. I will submit a grade estimate. The grades are going to be due a week from today, but you should have done your programming assignment, and we should have had our meeting. And so I'll be able to give you a grade estimate at that time, and we'll talk about it. You'll still need to take the exam on Thursday with the class as normal. And what I'll do is I'll update. Usually, unless you're right on the edge, normally, you know, we'll have like 70% of your grade by Tuesday. So normally it's pretty clear what grade you're going to get in the class by that point. But sometimes I miss, and if so, I'll just submit a change of grade form and fix it after the fact. Is the final cumulative? Yes, the final is cumulative. Students sometimes hate to hear that. They go, oh, God, cumulative final. But what you should do is you should heave a sigh of joy when you see that the final is going to be cumulative, because that means that a quarter or a third of the exam is going to be material you've already been tested over. So, so that's generally a good thing. Let's see. Haley. Or sorry, that's Cody, isn't it? Could you update the grade from the test and end up failing after we graduated? Well, I suppose that's possible, but I think once you've graduated, we pretty much can't take it back. But no, generally, graduating seniors, I've never had that question come up in all the years I've done this, Cody. Whether you're going to make a C or a B or an A, even a D or a C, that question comes up. But you know, I've never had the fail question come. I suppose I could give an estimated grade and the senior just decide not to show for the final, and I guess that could convert. I could convert it to an F. But I've never had anybody do that. And I certainly, if you're graduating, I don't suggest you do that. We can find out what the system will do in that case, I suppose. Do we get a cheat sheet for this one? Do y'all want a cheat sheet?
Yes, please. Double-sided this time, please.
Oh, you asked for an inch, and I say yes, and then you want a yard. We will 2 cheat sheets now. See, it goes from just a front to a front and a back to 2. I will allow a single-sided, handwritten cheat sheet. Single-sided, handwritten cheat sheet will be fine. I do think that it's good to have it, because it helps you guys learn, I think. I think I already told you guys, even in classes that I couldn't have a cheat sheet on an exam, I'd always make one out as I was studying, and it helped me. And then I would just read over it right before the exam and kind of memorize everything, and then I would just give it back on the exam. Kind of sad, since we're really supposed to learn and not just regurgitate. Okay. I'm not going to make the exams harder, Jonathan, just because people are asking for a cheat sheet. But yeah, have a cheat sheet. It'll make you feel better, and you can write down formulas and not have to worry about memorizing them. Anything else before we really dive into things? Okay. All right. So let me share my screen and start looking at the notes here. Okay. So again, at the top, I have my favorite Doctor Who quote for logic. Logic, my dear Zoe, merely enables one to be wrong with authority. Why do I put that there? Because yes, logic is good. Logical, if you construct a logical argument properly, it's not going to give you a wrong answer. The problem, though, is constructing the argument, especially translating English sentences into logic. You always lose subtlety of meaning when you do that, and sometimes that subtlety of meaning is critical. Also, too, when you get an answer, it's going to be in a logical formalism, and you have to convert that back into English. And the conversion process from English to logic and from logic to English, that's not an algorithmic process. It takes human intuition to do that currently. Someone can use logic and still be totally wrong, but with authority, because it sounds impressive, you know. Okay, so let's start with an example. We've already been playing with this example, which I'm now calling Mike's not wet outside warm day. And you'll recall that it started with three statements. Statement one is, if you go swimming, you will get wet. Statement two is, if it's raining and you're outside, you will get wet. Notice what we're doing there, we're making it clear that there are two different ways in this world that you can get wet. Swimming is only one of them. And you'll remember that we talked about the fact that humans often go wrong. And if you tell them, if you're swimming, you'll get wet, and then you say, but you're not swimming, a lot of times humans will come to the conclusion, oh, I'm not wet. Well, that's not a rule of logic. That's illogical, because as you can see from statement two, there are other ways that you could be wet. So just because you're not swimming doesn't prove that you're not wet, because maybe you're outside in the rain, as rule two says. That'll also be a way of getting you wet. Statement three, if it's warm and there is no rain, then we call that a pleasant day. And then you're not wet, you are outside, and it is warm. You'll notice from these logical arguments here that there's no sense of time, there's no sense of change. Logical arguments for propositional logic and even predicate logic kind of take place in a timeless world where change does not occur. There are logics called, one of them is called modal logic, that does attempt to deal with the concept that over time the truth values of underlying statements can change, but not in your base propositional and predicate logics. Okay, so these 6 statements can be roughly converted into these propositional statements, propositional logical statements. Again, I could have used P's and Q's and R's and things like that, but I'm using meaningful propositional variable names. So if you go swimming, you'll get wet is roughly swimming implies wet, okay? Or rain and outside together imply wet. And warm and no rain together imply pleasant. And we know that you're not wet, you are outside, and you're warm. Okay? So that's just these English sentences roughly converted into propositional logic. This last thing here will look like gobbledygook to you right now. But what it says is not swimming or wet as a unit, and not rain or not outside or wet as a unit, and not warm or rain or pleasant as a unit, and not wet, and outside and warm. That's one long statement, because these are ands, so all of the little parts are anded together. That's one long statement that is intended to encapsulate all 6 statements that we made here as converted into propositional logic here. So what we're going to be looking at, and this is, by the way, conjunctive normal form. It's called conjunctive because ands are called conjunctions in logic. right? Conjunction, junction. What's your conjunctions? And I don't know. Do any of you have ever heard of Grammar Rock? Conjunction, junction. What's your thought? Oh, wow. Okay. Schoolhouse Rock. That's a thing that actually has survived the generations. That was brand new when I was a child, and somehow it has survived the generations. And I'm just a Bill. Yeah, I wish more people watched that one because people just don't know how things work. My family has the VHSs. Okay. An and is a conjunction. So when you say conjunctive normal form, what you're saying is that you have all of these expressions and they're all conjoined together. They're all anded together. In conjunctive normal form, the individual expressions are either individual propositional variables like outside or warm, or they can be negated propositional variables like not wet, or they can be a series of ored propositional variables. So not swimming or wet, not rain or not outside or wet, not warm or rain or pleasant. So conjunctive normal form is a conjunction, an anding of disjunctions, ors. So every statement is a disjunction of either individual propositional variables or negated propositional variables. Okay, so it's a conjunction of disjunctions, and that is what conjunctive normal form is. So now what we've got to do is we've got to talk about, well, how do you get from this, right, to this? It's really not so bad. And here's our definition that I just said. Conjunctive normal form statements consist of a number of conjoined clauses joined by and, where each clause consists of either a single term or multiple disjoined terms, in other words, ored terms. Terms are either individual propositional variables or individual propositional variables that have been negated. So you can have negation, but it's got to be, it can't be over multiple things. You can't have like a whole expression negated. The only things that can be negated are individual propositional variables. Okay. So the first thing is, where do all these ands come from? Well, any collection of propositional statements are, what you're really saying when you write those statements is that all of them are true, right? We went back to that at the very beginning. We said, well, if you're going to do automated reasoning, right, if you're going to do rules of inference like modus ponens, modus tollens, chaining of implication, normally we do those only on statements that we know to be true. So what you're really saying here is statement 1 is true, and statement 2 is true, and statement 3 is true, and statement 4 is true, and statement 5 is true, and statement 6 is true. All of that together is true. Notice the word that I was using. It was 1 and 2 and 3 and 4, and we have a symbol for and it's these symbols right here. So that's the first thing. What we're really trying to say is 1 and 2 and 3 and 4 and 5 and 6, which we could rewrite using getting rid of the word and replacing that with the and symbol. Okay. So I said that the individual clauses are either propositional variables or negated propositional variables. So if we go back up and we look, 4, 5, and 6, 4, 5, and 6 are clauses that are already in the appropriate form. 5 and 6 are just individual propositional logic variables, and 4 is just a negated propositional variable. So we could take this and we could rewrite it this way. 1 and 2 and 3 and not wet, or, sorry, 1 and 2 and 3 and not wet and outside and warm. So the last 3 we've taken care of. Now, what about 1 and 2 and 3? Well, what are 1 and 2 and 3? I'll write them here so I don't have to keep going back up to the top. No, actually, they're in a different form there. Let's go back up to the top. 1 and 2 and 3 are all statements that include implication, right? And you'll remember from our last lecture that we said that P implies Q can be rewritten as not P or Q. And we proved it. We gave the truth tables that showed that they were equivalent in all cases. We showed that P implies Q is equivalent to not P or Q. So because of that, I rewrite it right there. Not P or Q is equivalent to P implies Q. So we can rewrite swimming implies wet as not swimming or wet. And we can rewrite rain and outside together imply wet as not rain and outside or wet. And we can rewrite warm and no rain implies pleasant as not warm and no rain as a unit or pleasant. So all we did here was use the equivalence that we learned last time to get rid of the implication and replace P implies Q with not P or Q. Okay. So let's look at these things. 1 now is in the right form. It is a disjunction. It is an or of 2 terms where one of the terms is negated. So you can have negated terms, but it's only terms that can be negated, only propositional variables. So not swimming or wet is fine. So right now we've got not swimming or wet and 2 and 3 and not wet and outside and warm. Okay, but what about these 2 guys here? Well, you might say, Mike, we got a problem because we got an and inside this term, and you're not allowed to have ands inside the terms, inside the clauses. You're only allowed to have ors. It's a conjunction of disjunctions. This is not a disjunction because there's an and in it. But we also remember that if you've got a not and it goes over not A and B, it's the same thing as not A or not B. So we can drive this not in across the rain and outside and get not rain or not outside. And we can drive the not here and get not warm or not rain. And what is not rain? It's just rain, right? And here you can see where we've done that. We've driven the not, so we got not rain or not outside, and we still have the or wet, right? And here we'll have not warm or not rain or pleasant, right? And of course, we know that the nots are going to go away because they cancel. So clause 2 is in its proper form, and clause 3 will be in its proper form as soon as we notice that not goes away. So we end up with, I had to make the font size smaller so it fit on one line, but we ended up with a disjunction, an anding of clauses where each clause is either a single propositional variable like outside or warm, or a single or a negated propositional variable like not wet, or a disjunction of propositional variables and ORing of propositional variables where some of them may be knotted and some of them may not be knotted. But this thing that we've got here now encapsulates in one logical statement all 6 of the original statements that we were trying to make, okay? And so now what we've done is we've converted this into conjunctive normal form. Now, you might say to yourself, Self, why is Mike showing us this thing? Because let's face it, it's a lot easier to read, the English. If you go swimming, then you'll get wet. If it's raining and you're outside, then you'll get wet. Or even once I've converted it into propositional logic using implication, it's still swimming implies wet, rain and outside implies wet. It's still close enough to English here that you can easily follow the story and see what's being said. But by the time you get to something like this, I don't have a clue as to what this thing means. It's so far away from the English now that it just looks like gobbledygook. Now, I know that it's got to be logically correct because, I followed the rules of logic. I used valid substitutions that we had talked about, last lecture. So I didn't do anything wrong. I know that logically this statement is logically equivalent to saying that all 6 of these statements are true. This and this have to be the same. They have to mean the same thing because all we used were rules that we had already proven that you could use as substitutions. Like not means not, and implication, P implies Q means not P or Q. So we had proven those things, so you can make those substitutions. So this says exactly what this says. Exactly. There's no difference between these at all. Now you can argue whether or not there are differences between the 6 English statements and the 6 things that I said here, right? And you can argue things like you're saying wet here, Mike, but here you said you are not wet, and here you said you are not wet. Where's the you? Well, there is no you. I dropped it. I'm just going to understand that all of these statements, when I'm making a statement, apply to me, right? And how about warm? A lot of things can be warm, right? Why didn't I call this warm day? I could have called it warm day if I had wanted to, as one word, WARMDAY, or maybe underscored if you wanted to do that. But so you can argue whether or not the English is truly captured here completely correctly here. But once we've gotten to these 6 statements, there's absolutely no argument that these 6 statements, when we take them all together as being true, is exactly the same as the statement that we got here. There can be no difference because we used logical substitutions that we've already proven to get from this state to this state. So we've taken something that we could pretty easily understand, and we've moved it to something logically equivalent that is almost completely alien to people. But you can kind of think about it as, translating a high-level language into machine code if you wanted to. So this is kind of our machine code of logic, if you want to think of it like that. Am I muted? I shouldn't be muted. Hopefully everybody is hearing me. If you're not, scream. Okay. So what I've just been saying is what I have here in my notes. Okay. So why are we doing this? Well, I already said earlier, we're doing it so that we can use resolution. Resolution is a proof technique that subsumes modus ponens, modus tollens, and chaining of implication. It can do anything that you can reason with these 3 things, you can reason with resolution. So how does resolution work? It consists of 3 steps. First, you select 2 clauses that contain conflicting terms. What do I mean by conflicting terms? Well, one of them would contain, say, A, and the other one would conclude not A. And you can cancel when you find conflicting terms. So you find two clauses that contain conflicting terms, you combine the terms together in those clauses, and then you cancel the terms that conflict. And the reason why you can cancel is something cannot both be true and not true at the same time. So because of that, no information is being added by saying A or not A. Think about that. If I say it is raining or it is not raining, what have I told you? Absolutely nothing. So if you've got a clause that contains both a statement that something is true and a statement is not true, well then, you know, it contains a statement is true or a statement is not true, then those two things together don't tell you anything, so you can just cancel them out. They're not giving you any information in that case. So let's now look and see how we can use these things to do the individual inference rules, chaining of implication, modus ponens, and modus tollens. So let's say I have two English statements. On sunny Sundays, I go to the beach, and I drink beer when I'm at the beach. So those are two statements. I'm going to assume that they're both true. Now, I need to get them into propositional logic. You will notice that on neither of the statements did I say, if A, then B. I used English that means that, but I wanted to show you that the English doesn't have to contain the words if and then. But when I say on sunny Sundays I go to the beach, what I'm really saying is, if it's a sunny Sunday, then I go to the beach, or I'm at the beach on a sunny Sunday. Could I go to the beach on a Wednesday? Yes or no in chat? Could I go to the beach on a Wednesday? Sure. Maybe it's a holiday, so I could go to the beach on a Wednesday. But on a sunny Sunday, if it's Sunday and it's sunny, I go to the beach. Now notice in this particular case, I indicated sunny Sunday as one term. Mike, why didn't you make that sunny and Sunday? I could have. But for my particular purposes right here, I decided that one proposition, meaning a day that's both a day that is a sunny Sunday, a day that is both sunny and Sunday, I would just encode that in one proposition. I can do that. Now, I can't reason about non-sunny Sundays if I do it this way, right? Or sunny days that aren't Sundays, because I've lumped all of that together. But for this particular example, I decided to show you that, in this case, I decided that the fact that it's both sunny and it's a Sunday, that I was never going to break those ideas apart, so I just used one propositional variable to mean sunny Sundays. I can do that. So sunny Sundays imply that I'm at the beach. Or another way you can say it is, if it's a sunny Sunday, then I'm at the beach. Or you could say, on sunny Sundays, I go to the beach. Those are all, the English is all approximately the same as what I'm indicating here. Also, I didn't say, if I'm at the beach, I drink beer, but that's what this means. I drink beer when I'm at the beach. So if I'm at the beach, then I'm drinking beer. Can I drink beer on the couch watching a football game? Of course I can drink beer on the couch at watching a football game. So being at the beach isn't necessarily the only time that I drink beer, but what I'm saying here is I do drink beer when I'm at the beach. If I'm at the beach, you can tell I got a beer in my hand, okay? So We have two statements here. Sunny Sundays imply that I'm at the beach, and at the beach implies that I'm drinking beer. So if it's a sunny Sunday, what can you conclude? If it's a sunny Sunday, what can you conclude? Oh, poor Alex Trebek passed away, but by the way, this weekend. So whenever I sing the Jeopardy song, now I think about poor Alex Trebek having passed away. What it obviously means is that if it's a sunny Sunday, then I'm drinking beer. Okay? But can we make resolution come to the same conclusion that any human would come to? Well, let's take these two statements and let's convert them to conjunctive normal form. So first, we're saying this statement and this statement. So that's where this and comes from. This can be written as not sunny Sunday or at the beach. Not sunny Sunday or at the beach. That captures on sunny Sundays, I'm at the beach, or if it's a sunny Sunday, I'm at the beach. And at the beach implies drinking beer. I'm either not at the beach or I'm drinking beer. I'm either not at the beach or I'm drinking beer, because if I'm at the beach, I'm definitely drinking beer. So I'm either not at the beach or I'm drinking beer. So now we've got two clauses, and notice that this clause contains at the beach and this clause contains not at the beach. Resolution says you can combine these two clauses together and cancel the conflicting terms. So when I find two clauses that have conflicting terms, I can combine them and cancel the conflicting term. So when I do that, what do I get? I get clause 3 that says not sunny Sunday or drinking beer. Not sunny Sunday or drinking beer. What would that mean as an if statement? Well, we could go backwards from not P or Q means P implies Q. So not sunny Sunday or drinking beer means sunny Sunday implies drinking beer. So what is chaining of implication? Chaining of implication says if you have something that says if A then B and if B then C, you can say if A then C. And that's exactly what we did here. Sunny Sunday implies at the beach. At the beach implies drinking beer. So implied in those two statements is a third statement. Sunny Sundays imply that you're drinking beer. If it's a sunny Sunday, I'm going to be at the beach. And if I'm at the beach, I'm going to be drinking beer. So if it's a sunny Sunday, I'm going to be drinking beer. Does that make sense? Does that make sense? I need some yeses. I need some hell yes. I need some interactions. Okay, good. Awesome. So we've just shown that this finding clauses that have conflicting terms, merging the clauses together, and canceling the conflicting terms does chaining of implication. It does exactly what chaining of implication does. It can find, if you give me two if statements where the conclusion of one is the premise of the other, I can give you a third if statement. Okay? So what about the others? What about modus ponens? Well, if I'm at home on a Sunday night, then I'm watching Walking Dead. Well, that used to be true. I got bored of Walking Dead. I don't know if any of you have. After Carl died and Rick went away, it's like, geez, I don't know. And it would always seem to be the same thing over and over and over. But I loved it in its early days, but it got old. But anyway, in logic, it's a timeless world. So in this timeless world, if I'm at home on a Sunday night, then I'm watching Walking Dead. And let's say it is also true that I am at home on a Sunday night. So if I'm at home on a Sunday night, I'm watching Walking Dead. And I am right now at home on a Sunday night. So what could we conclude? Modus ponens says, well, you can conclude that you're watching Walking Dead. You said if you're home on a Sunday night, then you're watching Walking Dead, and you also said that you're home on a Sunday night, and you said that both of these statements were true, so that must mean that watching Walking Dead is true. And we can do this with resolution. Not at home on Sunday night or watching Walking Dead, that's one clause, and at home on a Sunday night. So we can merge these two things together, these two clauses together, cancel the at homes on a Sunday night with the not at home on the Sunday night, and what are we left with? We're left with clause 3, we're watching Walking Dead. So conjunctive, by expressing these statements in conjunctive normal form and using resolution, I effectively did modus ponens. So I've shown chaining of implication, I've shown modus ponens. How about modus tollens? So remember, modus tollens is not if I'm at home on a Sunday night, then I'm watching Walking Dead, and not at home on a Sunday night. That's not what modus tollens is. Modus tollens is at home on a Sunday night implies watching Walking Dead and not watching Walking Dead. Modus tollens, it's the conclusion that's negated, not the premise. So if I'm at home on a Sunday night, then I'm watching Walking Dead. But I know that I'm not watching Walking Dead. So what does that mean? It means I'm not at home on Sunday night. We can convert these statements to conjunctive normal form, not at home on Sunday night, or watching Walking Dead as a unit, as a clause, and not watching Walking Dead. Take these two clauses, merge them together. The watching Walking Dead and not watching Walking Dead conflict, so they cancel, and that leaves me simply with not at home on Sunday night. I just did modus tollens. So I have now shown chaining of implication, modus ponens, and modus tollens. Frequently what we do when we're doing these things is we show them graphically. If we're going to do a proof where we show, if you're doing a resolution proof, often it's illustrated by showing the two clauses that are being brought together, and then underneath you write the resulting clause. So clause 1 and clause 2 can be merged because they share at the beach. One is negated, the other is not. And once you bring these two clauses together and cancel the conflicting terms, in this case you're left with not sunny Sunday or drinking beer, which was our chaining of implication. So we've already done these. I'm just showing that you can illustrate them graphically. Here's modus ponens illustrated graphically. Not at home on Sunday night or watching Walking Dead, and at home on Sunday night. The negated clause and the non-negated version of that clause cancel, and you're left with watching Walking Dead, which was modus ponens. Or if you're given the same if statement, not at home on Sunday night or watching Walking Dead, and the negated conclusion, watching Walking Dead, you can merge these two because they share a term in common where it's negated in one and not in the other. Those cancel, and we're left with not at home on Sunday night. Questions? Questions? At this point, I have showed you two very, very important things. I have showed you how to convert a collection of true propositional statements to one statement that covers all of the previous statements, where that one statement is in conjunctive normal form. And then I've showed you how you can use resolution to do modus ponens, modus tollens, and chaining of implication. Okay. So what are we going to do next? Well, we're going to tie this together with resolution refutation proofs. refutation because I'm going to refute something. A refutation proof is just another word for proof by contradiction, okay? It's a resolution refutation proof because I'm going to use resolution as the technique that I use in this refutation proof. So, like all proof by contradiction, we will start with what we want to prove, and we will negate it, and we will show that that negation causes a contradiction. And if our original statements were all true and consistent, then the inconsistency that we found must tie back to the assumption that we made. And so if that assumption leads to a contradiction, the opposite of the assumption must be true. Do I have any material that you could use to practice this? If you look at my textbook, the AI chapter of my textbook, it has a whole section on this, and that's where these notes come from. And I think I have some problems to work on in that section. So it's the AI chapter of the textbook that I made available for you guys. Okay. Other questions? Okay. So what are we going to do now? We're going to dive into resolution refutation proofs. Now, remember how I began this lecture. Logic, my dear Zoe, merely enables one to be wrong with authority. Now, logic works. The rules of the game do reflect how people reason, okay? But I said that the place we go wrong is a lot of times in our translation of English into logic, into propositional logic. I made 6 statements about a world that I wanted to reason over. When we begin the reasoning process, we assume that all 6 statements are true. I'm telling you they're true, but if you want to reason over these statements and come up with other statements that must be true, then the assumption that we started with has got to be true. So these 6 statements have to be true, and they have to be mutually consistent. In other words, I can't have one statement that says you're not wet and another statement somewhere else that says you are wet. Well, both of those things can't be true at the same time, at the same place, etc. Okay? But because of that, they are inconsistent. They are contradictory. Okay? So if you want to use resolution refutation proofs or any reasoning mechanism in logic to divine new facts from existing facts, then the statements you start with all have to be true and all have to be consistent. Does that make sense? If there's any inconsistency, if something says I'm not wet, maybe I don't say I am wet, but maybe I said swimming was true in these statements. Well, that doesn't look like I've said anything false, but if you think through the statements, you can see that if I'm not wet, then I can't also be swimming, because rule 1, if you go swimming, you will get wet, and swimming implies that you are wet. but 4 said you're not wet. So it's not just that the statements themselves are directly contradictory. You can't have that, right? But you could have statements that are inconsistent in that you say one thing, but other things you've said implied the opposite of one of the things that you said was true. So you can't have that. You cannot have inconsistencies built into your statements or pass off false statements as true statements, or what gets produced in the logical argument, while you might say it with authority, could be wrong. Does that make sense? Does that make sense? I acknowledge my receiving of this knowledge. Okay. All right. Okay. So let's look at our resolution refutation proofs. After I have said multiple times here, and I will repeat it one more time, for resolution refutation proofs to produce logically valid conclusions, the original set of statements that are assumed true must be consistent. The statements must not imply that some proposition is both true and false at the same time. Now, we're going to assume that that assumption is met, okay? If it isn't met, the game, you can still play the game, but the conclusions fall apart, okay? So, let's say that I've got a set of consistent statements where all of those statements are true, using the 6 statements that we've been talking about all lecture, okay? And let's also say that I want to prove that I am not swimming. I never said that I'm not swimming here, right? If you go back to our previous lecture, I used modus tollens with 1 and 4 to conclude that I was not swimming. So I'm definitely not swimming. If all 6 of these statements are true, I'm definitely not swimming. And like I said, I did prove it last lecture by taking 1 and 4 and using modus tollens to prove that I was not swimming. So let's redo that with the resolution refutation proof. So I want to prove that I am not swimming. Okay? That's what I want to prove. Since I'm going to do a proof by contradiction or a refutation proof, I'm going to refute something. I'm going to make an assumption and I'm going to refute it. Okay? I will assume that I am swimming. Now, assuming all of the original statements were consistent and true, if I assume swimming, I have just introduced a contradiction into the system. The refutation proof will find that contradiction. Okay? So, how can we prove that swimming causes a contradiction? Well, you take swimming and you take not swimming or wet. You take the 2 clauses, you put them together. The swimming and the not swimming cancel, so that leaves us with wet. Great. But the system already has statement 4 in there that says not wet. Combine these 2 together and cancel the conflicting terms, and what do you get? You get a null clause. A null clause means that you have reached a contradiction. Okay? In other words, you're saying nothing is true or everything is true. Anyway, either way you want to look at it, when you get a clause that is null, is empty, there are no more propositional variables, that is how you detect a contradiction in resolution refutation proof. So you can see how this can be automated pretty easily, right? You are just doing, you're just taking something you want to prove, you're assuming the opposite, You're using resolution to put these clauses together, using clauses that have, or one clause has the positive version of the term and the other clause has the negative version of the term. You put those two together, you cancel the conflicting terms, and you keep doing this until you get a contradiction. If you get a contradiction, which you're not guaranteed to do, but if you get a contradiction, then you can know that swimming, the thing that you just said, caused the contradiction, because we're assuming that before you added this thing, everything was true and consistent, right? True and consistent. So when I added this new, quote, fact that turned out not to be true, that introduced a contradiction, that means the opposite of that fact must be true. It must be true that you're not swimming, because if you add swimming to all of the things you know to be true, you get a contradiction. Let me say that again. You know that not swimming has to be true, because if you take its opposite, swimming, and add that into the group of statements that you know to be true, and that new statement, swimming, causes a contradiction, it's the only thing you changed. It's the only new thing you introduced. So if that new thing you introduced caused a contradiction, that new thing has to be false, which means its opposite has to be true. Is that reasonable? Is that reasonable? Yes, no, maybe. Yes, no, maybe. Yes, I got one yes. I got an indeed. I got another yes. I got a yepperinos even. That's fantastic. Oh, I put this back in English. I'll say it again for about the 5th time because it's so important. To prove that you are not swimming, we will assume that you are swimming and show that that assumption leads to a contradiction. Statement 1 says that either you're not swimming or you're wet. But since we are assuming that you are swimming, then logically you must be wet. However, statement 4 says you're not wet. Hence, we found a contradiction. If all of our original statements were true to begin with and not inconsistent, true and consistent, our assumption, you're swimming, must be incorrect. So we conclude the opposite, that you are not swimming. And that's how resolution refutation proof works. We can use another one. We can prove that it's not raining. How can we prove that it's not raining? Well, assume that it is raining. Assume rain. And if you look around, you can find that clause 2 says not rain or not outside or wet. You can combine those together. The rain and the not rain cancel, leaving you with not outside or wet, right here. Statement 5 says you're outside, so that if you merge our new statement, our new clause, and outside, you get wet. But we have a statement 4 that says not wet, so when you merge these, you get the empty, which is a contradiction. So rain causes a contradiction. It is inconsistent with what you know. Rain is inconsistent with what you know. So if, when you began this process, everything was true and consistent, everything that I thought was true is true, and all of those statements are consistent, there are no implied things that are false, then adding rain caused a contradiction, so its opposite must be true and consistent with what I know. It is not raining. And finally, let's do pleasant, okay? Well, rather than me go through pleasant right now, why don't you go back to our 6 statements and try to prove pleasant. So take about 5 minutes grab a sheet of paper. So if you're ordering chicken wings, pull off to the side and get out a piece of paper, right? And I want you to try to prove pleasant using a resolution refutation proof and these 6 statements, or whichever of those 6 statements that you need. Okay? Take about 5 minutes. I'll take a quick break, and we'll come back and we'll see how far you guys have gotten. Okay, are we ready to move on, guys and girls? Okay. Okay, so here's what I came up with. We want to prove that it's a pleasant day. So we assume that it's not pleasant. The only statement that mentions pleasant is statement 3. So which says not warm or rain or pleasant. So if you combine not pleasant with statement 3, you'll get not warm or rain. Well, statement 6 says that it's warm, so that gives us, when you combine the 2, that gives us rain. But we also know that not rain or not outside or wet is true. So if we combine rain, and actually you could refer to the one we previously proved it if you wanted to, but I drove it all the way through. So rain and not rain or outside or wet, the rains vanish, and that gives us not outside or wet, which goes with outside, which gives us wet, which goes with not wet, which gives us our contradiction. Anybody have problems with that? or did it go through? Okay. All right, so that's basically resolution and resolution refutation proofs. Now, what I wanted to do next was I wanted to talk about horn clauses. Now, what I'm doing here is I'm beginning to introduce a simplified form of prologue. So far, all we've done is we've talked about propositional logic. Prologue doesn't use propositional logic. Prologue uses predicate logic or first order logic, which we're going to talk about on Thursday. But you can still introduce all of the basics. So if you were to look at another professor's notes or another textbook, they wouldn't have introduced. They would have already have introduced first order logic before they introduced resolution and resolution refutation proofs and horn clauses. But you can introduce all those things with the simpler propositional logic like I'm doing, and then once everybody knows about resolution, resolution refutation proofs, and conjunctive normal form, you can jump over to first order logic, and 90% of everything that I've already taught you works perfectly well in first order logic. I do it this way because it's a little simpler to introduce it this way, and we don't get hung up on the existential and universal quantifiers. We'll talk about what those are on Thursday. We don't get hung up on those first, and so I like to do it this way. Okay, everybody has their own little way of doing things. So what I'm introducing is something called horn clauses, the horn clause notation, the horn clause subset of conjunctive normal form, and it is essentially the format that's used by Prologue. Okay, so that's what we're doing. We're beginning to talk about what's called horn clauses. It's a subset of conjunctive normal form, and it is the format that Prologue is based off of. Okay. So, what are horn clauses? What is the horn clause subset? So that means that it's not going to be all of conjunctive normal form. It's going to be a subset. Well, the horn clause subset of conjunctive normal form is exactly conjunctive normal form. It's a conjunction, an anding of clauses, where each clause is a disjunction of terms in which all of the terms in the clause, save at most one, are negated. In horn clause subset of conjunctive normal form, you're only allowed to have at most one non-negated term. Okay, so let's go back and let's look and let's see where we already in horn clause notation. Well, this has one non-negated condition, and this has one non-negated condition. These two are negated. But this one has two non-negated conditions. So this is not actually in the horn clause subset of conjunctive normal form, because I have two non-negated clauses, and I'm really only allowed to have one non-negated clause. Okay, but 1, 2, 4, 5, and 6 are all valid for the horn clause subset. Come on, Micah, as you scroll through all of this. Okay. So prologue uses the horn clause subset of conjunctive normal form, but it expresses things in terms of facts and rules. Okay, a fact is just a true statement. A rule is a conditional statement. It's an if statement. And to make things a little difficult, because where computer science types are difficult, the syntax of prologue is head if body, which is really conclusion if premise, and the if is written as a colon and a hyphen. So that colon hyphen means if. So conclusion if premise, head if body. So like instead of saying if A and B and C are true, then Z is true, well, you would write Z if A, comma, B, comma, C. The commas mean and. So you have facts and you have rules. Z if A and B and C. Now at this point you should be saying, okay, Michael, I'm thoroughly confused because you led off by saying that prologue uses the horn clause subset of logic, of conjunctive normal form, right? And this doesn't look anything like conjunctive normal form, and you're just reading these commas as ands here. What's going on? Well, I will explain. Okay. How can Z if A and B and C, right, be a horn clause? Well, what I'm writing is Z is true if A and B and C are true. So let me flip it around. If A and B and C are true, then Z is true. These all mean the same thing. Z if A and B and C, Z is true if A and B and C are true. If A and B and C are true, then Z is true. So, and while I don't have it here, right, a lot of times we could just add parentheses because everything before the then, right, everything that you and together before the then is a statement, right? So we could put this back into the form of a more normal looking implication statement as A and B and C as a quantity implies Z. So when we say Z if A and B and C, we're really saying if A and B and C, then Z. Okay, I know we're going through a lot here, but let's say that we get rid of the implication now. How do you do that? Not premise or conclusion. So not A and B and C or Z. Well, I've got to drive that not over this expression. So not A or not B or not C or Z. Really is a horn clause. It's a conjunction, right, of terms where there is at most one non-negated term. Does that make sense? So prologue statements have this form. Something is true if blah and blah and blah are all true. But that form is reflected in the fact that you only have one non-negated term in your disjunction. You can't have more than one positive term. What does that mean? It means that you can't have a prologue statement that says Y or Z is true if A and B and C. You can't say that in prologue. You can't say Y or Z is true if these other things is true. You got to be able to conclude one thing based on whether some other things are true. So you can only have one term, one conclusion to your if statement. And because of that, that means that you can only have one positive term there. Okay? That's where that restriction comes from. In prologue, your if statements, you can have, if A and B and C are true, if A and B and C and D and E and F are true, then Z is true. But you can't say, given these conditions, this or that is true. If I have a fever and a cough, then you can conclude that you have a cold. You can write that in prologue. You can't write in prologue, if I have a fever and a cough, then I have a cold, or I have the flu, or I have COVID-19. You got to conclude one thing. You can't conclude, oh, it could be this bunch of things here. Prologue doesn't allow that. Okay? Now, and I say that here, since there is always a single conclusion in the head of a prologue rule, each prologue rule always translates to a single clause that is a disjunction and oring of terms in which one and only one term is negated. So if I'm doing a rule, if I'm doing a prologue rule, I'm going to have one and only one term that is positive. And so here I have four little rules. These all get down to four terms or four clauses that are in conjunctive normal form. I didn't do the last step here, which should have been not raining or not outside or wet. All right, that's one thing. Not swimming or wet. That's one positive thing. Raining is positive, outside is positive. Okay, and here you can see our little resolution refutation proof of it being wet. Okay. Now, I started talking about the expressive limitations of prologue, and I'll jump down to the last case, which I said you can't do in prologue. You can't have disjoined conclusions. Prologue cannot express something like, if A, then either B or C is true. So I cannot say something like, if I'm going on vacation, then I will experience fine dining or I will gamble. Notice I didn't say and. I didn't say I'd do both of those things. This is trying to say you're going to do one or the other. You can't express this in prologue because what you're trying to say is vacation implies fine dining or gambling, which is not vacation or fine dining or gambling, and you have two positive things here. So that's not a horn clause. You can't write something like that in prologue. Fine dining or gambling if vacation. And I misspelled vacation, didn't I? So you cannot have a disjoined conclusion, because to do so, you would need more than one positive propositional variables in your horn clause. Is that a limitation? Yes, it's a limitation. Is it a huge limitation? Only if you want to say the things you can't. You can usually find ways of saying something you could glom together the concept of, just like I glommed together Sunny Sunday, where I had two things and I put them together and I said, oh, in this case, I'm just going to encode these things as one thing. You could encode fine dining or gambling as one term called fine dining or gambling, and then you could make it work, but you can't break it apart in that statement. Okay, now let's look at some other things that you can do in Prolog that maybe you thought you couldn't do. So you can definitely have conjoined premises. You can have multiple things in the premise, all of which must be true. So you can say if A and B and C and D and E, then Z, or if A and B, then C. So an example is you could say something like, if smart and funny, then likable. The person's likable if they're both smart and funny. So you can write this as smart and funny implies likable, which translates into not smart and funny or likable, and then you drive the not in, not smart or not funny or likable. And so that is a horn clause, and so it can be written in our little propositional prologue as likable if smart, comma, funny. Also notice prologue statements end in a period because they're sentences, so we always end them in a period. So yeah, you can express this concept of if A and B, then C in one prologue statement. So you can have multiple premises that are conjoined together, that are joined by and that translates into one statement. How about disjoined premises? If I wanted to say something like, if A or B, then C, could I do that? Can I write that in prologue? So I'm trying to say something like, if it's raining or it's cloudy, then take umbrella. It's clearly something we would want to say. If rain or clouds, then umbrella. Well, that would become rain or clouds as a unit implies umbrella. And that would become not rain or clouds or umbrella, right? But now this is something we've not seen before. We've seen when you've got something like smart and funny, the not flips the symbol over into an or. But what happens if we start out with an or? Not rain or clouds. When you drive the not through, you get not rain and not clouds. That ain't a clause in conjunctive normal form. In a horn clause, it's not even in conjunctive normal form, because this guy has an and inside it, and it's not supposed to. The clauses are all supposed to be disjoined. But here's another little trick that you can do. You can, if you've got, and we're going to talk about these tricks again next time. If you've got something that is an expression that's anded, and then there's an or element to it, you can distribute the or over the and actually get two disjoined clauses that are conjoined together. So not rain and not clouds or umbrella becomes not rain or umbrella and not clouds or umbrella. You're distributing the or over the and. That's a distributed rule that you have in logic. Well, now that I've got this, you can see that actually you can write it as two separate prologue rules. This one says, basically, take your umbrella if it's raining, and this one says, take your umbrella if it's cloudy. So I needed two rules to write it in prologue, but it says exactly what, well, I guess this is it. It says exactly what we've got here. If it's raining or it's cloudy, then take an umbrella. I can write that as, if it's raining, then take an umbrella, and if it's cloudy, then take an umbrella, which is exactly what I did here. So you can have conjoined premises, like we showed in step 1. You can have disjoined premises, like we showed here. The only difference is if you've got disjoined premises, you get two rules that both conclude the conclusion of the rule you're trying to write. So it's okay to say if A or B or C or D or E, then F. That'll just become F if A, F if B, F if C, F if, etc. Okay? So you can capture conjoined premises, you can capture disjoined premises. How about conjoined conclusions? Can we say something like, if Conan, then big and strong, right? Conan is both big and strong. So can I say something like this? If Conan, then big and strong. Can I have conjoined, anded conclusions? So in general, I'm trying to say something like, if A, then B and C. Can we do that? Well, let's convert it and see what happens. Conan implies big and strong. Not Conan or big and strong. Well, we've got the same kind of thing that we had before. We've got an or that we need to distribute over an and. So that becomes not Conan or big and not Conan or strong. So you've got two rules. I can conclude big if Conan, and I can conclude strong if Conan. So you can do conjoined conclusions. It just takes two rules. So basically, if you have disjoined premises, you get two rules that have the same conclusion. If you have conjoined conclusions, you get two rules. They have the same premise, but different conclusions. And that brings us back to the one case that we can't do, which is we cannot have disjoined conclusions, because that breaks prologue. It doesn't just break prologue. The reason why it breaks prologue is because this expression cannot be written as a disjunction of terms where at most one is positive. It takes two of these terms here to be positive, and you can't express it. So the only thing you can't do in prologue is say something like, if I've got a premise, I can conclude this thing or this other thing. You can't say that directly because it's not set up for that. Doesn't mean that you can't come up with a term that gloms this idea of A or B together, and maybe that'll be enough to get you around the problem. Okay. Questions about that? Questions about that? Questions. Now, you can't tell me that all that made perfect sense and there were absolutely no questions there, because it is a bit. It's more than a bit. It's a bite. It's more than a bite, right? It's a double bite. It's a word. It's not a bit. It's not a bite. It's at least a word worth of knowledge that I've departed on you guys here. Okay? I do want to my contradictions aren't apparent at the moment. Okay, good. I've been talking about the fact that next time we're going to talk about first order logic. And I've also been saying multiple times that, well, I'm showing you kind of the format of prologue. but I'm leaving out the fact that Prolog doesn't work on propositional logic, it works on first order logic. Let's take a few minutes now to kind of give you an aperitif of what we're going to cover, isn't that a fancy word, of what we're going to cover next time, okay? A little dim sum, a little tapas of what we're going to cover next time. Now I'm talking about food. I'm hungry. I'm going to have to make myself something to eat after this. Okay. So, as I've hinted, there are other logics. And the most common is first order logic, okay? First order logic, or prepositional logic, it's sometimes called. If you wanted to look at a real Prolog rule, a real part of a Prolog program, you might run across a statement like this. What is that statement saying? It's saying X is the mother of Y if X is the parent of Y and X is female. That makes sense. Your mother is your female parent, right? Your mom is your female parent. So X is the mother of Y if X is the parent of Y and X is female. This is true Prolog. You see the format's still the same. One conclusion, if, a, and then there's a comma there, which means and then there's the next thing, and then there's a period at the end. So the only thing we've built is we now have these relations, okay? So instead of just a single variable, you can have relations in Prolog. And that is the big, big difference between propositional logic and predicate logic. In propositional logic, you just have individual variables that have no, that's just all you have, is single individual variables. But in prepositional logic, you have prepositions or relations that represent, you can almost think of them as representing functions. They are, they represent relationships between two things. X, mother of Y, is a relation that you can express inside the logic. X, parent of Y, is another relation you can express. These relations can be multi-valued or single-valued, like female, only is a single-valued relation, where parent and mother and equal and all of those things are two-valued. Okay, so as I said, Prolog is really based on what's called first-order logic, which does allow the use of these variables. Another bit of Prolog syntax: the relations are lowercase and the variables are uppercase. A little bit of Prolog syntax. So why first order logic rather than propositional logic? I've said this before at least once or twice, but here it is in the notes, and let's think carefully about it. A typical syllogism that you see at the beginning of a logic class is Socrates is a man, Plato is a man. Okay, so I could represent this in, you might say, well, Mike, I can write this in propositional logic. You've showed me how. I could say something like Socrates man or Plato man, right? I can use a variable for this statement and a variable for this statement, and everything is fine. And that is true. I could, if I wanted to say Socrates is a man, if I wanted that to be true, and I wanted Plato is a man and that to be true, I could encode each of these statements in a propositional logic expression in a variable. But I haven't really done anything because when I say these to you, right, to a human that speaks English, you understand that I'm saying that Socrates and Plato have something in common. They are both men. Now, I'm using this old sexist terminology is generally what's used in these classes. Today, we'd probably say is a person, right? Socrates and Plato were both males, but what I'm really trying to get at here usually is human being, right? So a lot of times you'll hear me say man, and I mean person, but the idea is that Socrates and Plato are both people, and that's completely missed here. I could just as easily have called this thing P and this thing Q. There's no relationship between Socrates man and Plato man. What we want is to say something like this. The relation man, Socrates is an instance of that. Also of the relationship man, Plato is an instance of that. So if we did that, we could say that man Socrates was true and man Plato was true. We're now telling the system that Plato and Socrates are instances of the relation man or of the class man. And that's very, very powerful. And one of the reasons why it's powerful is it lets you say things like, all men are mortal, right? I can say something about mankind. If you're a human being, if you're a man, then you're mortal. You're going to die at some point, okay? I could, if I were to encode this idea, and I haven't shown you how yet, but if I were to encode that, all men are mortal, then I would be able to conclude that Socrates is mortal and Plato is mortal and any other instances of man that I chose to list out. So you can make general statements about a class. I really should go through and change it to person, but again, the standard is using man here. But do you see that I'm making a huge point here? A huge point here, that you can make statements about entire classes of objects, where before, with propositional logic, you can't do that. Everything is its own little proposition, its own little variable. And there's no way that you can talk about a group of items, where with first order logic, you can talk about a group of items. So you can talk about something being true of all of the members of the group. All men are mortal, and we're going to come up with something called a universal quantifier that captures the idea of for all. And there's also something called an existential quantifier, which means there exists, and that allows you to make statements about individuals in a group. So you can say something like, some people like Star Wars. So what's that saying is that there's at least one person that likes Star Wars. It's not saying that all people like Star Wars. A lot of people do, but some people don't. So propositional logic, first order logic, prepositional logic, allows you to talk about groupings, to talk about relations, okay? And you can say statements. You can say a statement is true for all members of a class, for all members of a group, or you can say that something is true for particular individuals. You can name them like Plato and Socrates, or you can say, I don't know the names, or I'm not telling you their names, but there are some, at least one member of this group for which this other thing has to be true. And so that gives you a lot of expressive power that you don't have with propositional logic. You can tell more complicated stories and you can reason about more complicated situations using first order logic. Does that make sense? And that is what we're going to talk about on Thursday. I'm going to introduce the existential quantifier, the universal quantifier, these relations, and then we're going to go through the same kind of exercise that we've gone through this lecture and the previous lecture, where I take a story in English, I show you how to convert to first order logic. I then show you how to convert that first order logic into conjunctive normal form. We then do some resolution refutation proofs with first order logic in conjunctive normal form. But I can do that all in one lecture. It's taken us 2 lectures to get here for propositional logic, but 90% of everything is going to be the same. 80% of everything is going to be the same. There are all going to be some new things that you're going to have to know for first order logic, but pretty much everything that we've said about propositional logic and our little propositional logic version of Prolog will hold. And then on Tuesday, on our last lecture, we're going to actually, I'll run some Prolog programs and we'll actually talk about Prolog as a language. And you'll be able to see, yeah, it's a logic language, but it's also a standard cursive language. And the cool thing about Prolog is you don't, when you define a function or a relation, you don't specify which variables are input and which are output. So it defines a relationship between variables, but what you choose to have as the inputs and what you choose to have as the outputs can vary. So you can write a little program like, oh, I don't know, concatenation, that takes a bunch of things and concatenates them together, or you can give it something and it can deconcatenate it. It can give you all of the examples of all of the things that can be put together to form this concatenation. So it runs backwards. You can run backwards. Okay, questions, let's see. This is the kind of logic that we can build in AI in a few months by the end of the summer at the latest. Exactly, Jonathan. I love that statement because you can see with what we've done over the last 2 lectures and what I've described as what we're going to do in the last 2, you can see how people were seduced into thinking that they were going to be able to solve general purpose intelligence because they had a roadmap. We've got formal logic. We know about conjunctive normal form. We know about resolution. I think those things had been invented by that time. So, sure, we can automate this. Give me, half a dozen smart people in 3 months, and yeah, our graduate students can clean up the dead ends that we don't cover. That'll be good. Give them something to do, and maybe they can get their PhDs out of it. But yeah, that's basically it. And remember, we talked about Doug Lenat, right? And his Psych project. Remember when we were doing the history of AI, and I showed you some snippets of Doug and his Psych project. Psych is just it's built on first order logic and our resolution refutation prover. It's a lot more complicated than that. There's a lot of special things they've done to make it run faster and blah, 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 blah. They haven't been sitting on their hands for 30 years or whatever they've been working on it. But yeah, that was the idea. That was the idea, that we can use logic if we just build a big enough knowledge base of common sense facts. We will be able to create an artificial general intelligence that can reason about the world. Once we get a certain level, it'll be able to read books and it'll become a super intelligence. Didn't happen, but that's the deal. Any other questions? Okay, I'm going to kill the recording right now. If you have additional questions, stick around and ask them. But for the rest of you, I will see you in the next video or on Thursday, whichever comes first. Take care and have a good day. Bye-bye.